Welcome back. This is part 3, which is going to be rather long and tough, in which we discuss Wegener's harmonic approximation. This is sometimes called spin wave approximation or Gaussian approximation. Okay. And as I discussed in part 1, this was discovered by Franz Wegener and then rediscovered by Berezinski, who did not know about Wegener's work. And he also did more, and he discussed how this approximation will break down. Okay, but anyway, the approximation itself was discovered by Wegener, so it's quite fair to call it Wegener's harmonic approximation. But unfortunately, this particular work by Wegener was sort of forgotten, and there are many articles in which this approximation is called Berezinski's harmonic approximation. And I'm sorry, this is my own book. I didn't know about this history. So anyway, now I know, so I'm calling it Wegener's harmonic approximation. Okay, anyway, let's discuss this approximation. Okay, so you already know the definition of the XY model. So we are interested in the very low temperatures situation. So let's consider first the zero temperature case, the ground state. And we examine what are the ground state, what are the minimum energy states. It's quite simple. When H equals 0, then we only have ferromagnetic interaction. So all the spins wants to point in the same direction. So there are many ground states, but so this is theta is simply arbitrary, and you require that everybody is pointing the same direction, theta. Okay, when H is non-zero, H is strictly positive, then because of this magnetic field term, all the spins wants to point in the positive x direction. This means that theta is 0 for all u. Okay, now what happens for the very, very low temperature? Then we expect to see configurations which are close to the ground states. Okay, when H equals 0, we expect that the difference between theta in the neighboring sites are very, very small. And when H is positive, then we expect that this absolute value of theta itself is very small for all u. And of course, we have this. Okay. Now we want to this is the same Hamiltonian. We want to rewrite the Hamiltonian this way by putting this -1 here, and just instead of here we add this constant here. And oh yes, in this lecture, whenever you have a finite set S, then this denotes the total number of elements in this finite set S. So this is simply the total number of bonds. So this is probably 2d times L to the d. This is the number of sides, so this is L to the d. But anyway, you don't have to care about this. These are just constants. Okay, then I think you can guess what we are going to do. We simply Taylor expand this cosine and just keep the leading term to write this very approximate Hamiltonian. And also, since we only care about theta, which satisfies this or this, the original range of theta is between minus pi and pi, but we simply replace this by just real number, just r itself. And of course, these are very bold approximations. You cannot say that this is valid when temperature is in this region or so. So this is a very bold approximation, but sometimes you get some very good physical picture out of such very bold approximation. Okay, now anyway, so these are just constants. So this is the main part of our Hamiltonian. So let's call this this Hamiltonian. So this is G stands for Gaussian. This is our Gaussian Hamiltonian. Okay, and so here's the summary for this approximate model. So first of all, this is the origin. This is a variable, but our spin variable is now theta u, and which takes value in the real number. Okay, so this is a very simple scalar field theory, and that is okay. So the collection of all theta is denoted this way, and this is our Hamiltonian. This corresponds to the action of massive free scalar field. But anyway, this is a Hamiltonian that we obtained from this Taylor expansion. Yes, and the partition function is here. So instead of summing over all possible spin configuration here, we simply integrate over all theta from -infinity to infinity. Okay, and so this is partition function, and this is the equilibrium expectation as usual. Okay, so this is the Gaussian model. Now we want to derive something that I call the basic identity for the correlation function in this Gaussian model. Okay. So this is identity. So, oh, yeah, this is the identity. How do you derive this? Well, first of all, I note that if you differentiate this Gaussian Hamiltonian by theta u, you get this simple form. Yes, because the Hamiltonian is this simple form, you get this thing. And here, this n of u is defined in this way. And this is simply, it's easier to see this picture. If this is u, then NU is a set of these green sites. So this is a set of neighboring sites, the sites which are neighboring to U. Okay. And then we look at this expectation value, theta v times this thing. This complicated thing is, but this is nothing but the right-hand side of this. Okay. So by using this, I can rewrite this expectation like this. Okay. So this is simply, you can just replace this by this, and then you want to consider the expectation value of this quantity, but by definition, it's written in this way. But now, if you look at this, here you differentiate this by h, and here you have e to the minus beta h. So you can rewrite the same thing in this way, right? You differentiate this thing by theta u, and you need this extra factor, but anyway, you have this. And then this is nothing but a simple integration by parts. You can rewrite this in this way. Okay, so this, now you differentiate this theta b by theta u, you get rid of this minus, and then, but this is just Kronecker delta, and then after Kronecker delta, this is just a definition partition function, so you simply get this. Okay, so we have a simple non-trivial identity for correlation function, which is written in this way. Here, this is a bit strange notation, but I regard, so here, this is just a 2-point correlation function. So the role played by V and U are symmetric. Okay, but I here sort of regard V as fixed and denote this 2-point correlation function in this way. It's a bit strange, but let me write in this way. And then this identity here is written like this. The right-hand side is, of course, the same. And as for the left-hand side, we have theta b times theta u, and theta v times theta w, and so on. So you can have this identity. Okay. Yes. Okay. So this is the definition, and this is the identity that I derived. Okay. Now, well, we can simply analyze this, but it's better to rewrite this by using something called the lattice Laplacian. This is a standard object, and this is just a matrix which is whose indices, whose components are denoted by, characterized by u and w in these lattice sites, and it's defined in this way. Diagonal has minus 2d, and off diagonal has 1 if v and u and w are neighboring, and 0 otherwise. And you can just easily convince yourself that this is a lattice version of your familiar Laplacian, which is sort of the second derivative. Okay, and then you can easily verify this relation by simply just considering this summation and comparing this and so on. So this is just easy. So you can just rewrite this by using this Laplacian like this. And then this is, of course, this part of this basic identity. So this identity can be rewritten by using Laplacian in this way. Or if you prefer matrix notation, this is Laplacian as a matrix, and this is an identity matrix, and this is UW component. Okay, so this part is written in this way. Okay, now then this is simply you have a vector G, and you multiply this by this matrix, and you get this new vector. So no. And so if this is invertible, then you can easily solve this and to find that there's a unique solution for this. And actually, this is invertible because I will show in the next page that this matrix minus delta is positive semi-definite, or the eigenvalues of this matrix minus delta are all non-negative. I'm going to prove this in the next page. So this means that the for positive H, eigenvalues of this real symmetric matrix is always positive. So this is invertible. So this G has a unique solution for G, and it's written formally in this way. So this is the inverse matrix. Okay, and since this is just a delta, Kronecker delta, you can just take sum, and so this is written in this way by using this the inverse matrix of this thing. Okay, this is just a formal solution, but it's very nice to know that this identity has a unique solution. Okay, so let me show some basic properties of lattice Laplacian, including this property about the eigenvalues. Okay, so this is a definition of the lattice Laplacian, and you clearly see it's real symmetric, so you can diagonalize, and you also see that eigenvectors form an orthonormal basis. Okay, and we claim that for any f that takes complex value, this identity, simple identity, is valid, and this is useful. And this is basically integration by parts time formula. So this I think this reminds you of this simple formula for usual function prime squared dx. Okay, so this is basically parallel to this thing. And the derivation is just simple, and I think it's easier to start from the right-hand side, and you simply expand and organize this part and this part separately, and rewrite it in this way to find that it's equal to left-hand side. It's easy, and this tells you many things. First of all, so this is of course always non-positive. So this thing is non-positive, but yes, this is of course Laplacian sandwiched by the same function f, same vector f. So this means that all the eigenvalues of delta are non-positive. Okay, also from, we don't use this one, from this definition, you find that if you sum over all w, you get 0. This means that this 1, 1, 1, 1, 1 vector is the eigenvector with eigenvalue 0. Okay. Finally, we can show that the eigenvalue is non-degenerate, and again from this identity. Well, so this identity tells you that this thing, again, this is Laplacian sandwiched by the same vector f, is equal to 0 only when f is constant, because the lattice is connected. Okay, so this means that this eigenvalue 0 is non-degenerate, and all other eigenvalues are strictly negative. Okay, we only used this in the previous page, but anyway, it's useful to know all these properties. Okay, so let's go back to the examination of spontaneous magnetization. So this is the spontaneous magnetization for the Gaussian approximation, and well, this is just the same definition. Here's the expectation value of the magnetization density in the x direction, and you take the infinite volume limit, and then let h go to 0. Okay, again, by using the translation invariance, you can rewrite this in this way. Okay. So we are interested in this expectation value. Okay, and then as we discussed before, this is the same as the expectation value of e to the I theta v. V is any fixed site. And then we claim that this is exactly equal to this. And if you're not familiar with this identity, I think you're surprised, but this is valid. And this is valid only for the Gaussian integral. And I will prove this separately at the end of this lecture. But if you want to know, then you can just go to the end of lecture and then come back. But anyway, this is the exact identity. And what is this? So this is the expectation value of e to the I theta. And then I said that it's exactly equal to exponential minus 1/2, and here's the expectation value of theta v squared. Okay, so that's theta v. So in our previous notation, this is equal to e to the minus 1/2 GVV. Okay, so we are interested in this. So if you know GVV, then you know this, and then if you take this limit, then you get this spontaneous magnetization. Okay, so we want to solve this basic identity, basic equation for G, and we just want to fix V and just write this simply as this. And then this basic equation is written in this way by using Laplacian, or if you write down the component of Laplacian explicitly, you can write it in this way. Here, EJ denotes the eigenvector, unit vector in the j's direction. Okay, so this is the equation that we want to solve for G. Okay, and so yes, for this, I think this is very standard. We use the standard Fourier transformation for on the lattice. So this is the K space, or the space of wave number vectors corresponding to the lattice. And here, this is the wave number vector, and each component takes this value of this form, where n runs roughly between minus L/2 and L/2. So this K itself is roughly between minus pi and pi. Okay. And then these are the basic identity. Okay, K dot U denotes usual inner product. And if you sum e to the I k dot U over U and divide by L to the D, and then you get the Kronecker delta for K. And likewise, if you sum this over K and divide, and then you get Kronecker delta for U. And these are very easy because these are simply geometric series. So just high school mathematics allows you to prove this. Okay. And now this is the definition of the Fourier transformation of GU. This is the Fourier transformation. And then you can prove by using probably this or this, anyway, this or this, the inverse Fourier transformation is explicitly written in this form. Okay, so now this is the equation that we want to solve. And then what we do is very standard. We simply substitute this inverse Fourier transformation here, here, here. Okay, and it's just the same here, but if you substitute it here, this becomes e to the ej, and this becomes e to the j. And then this becomes the product of e to the ik dot u and e ikj. Okay, so by this, I just changed k to k prime. So by substituting this, we get this. Okay, the left-hand side is equal to this, and right-hand side is touched the same. And let me write this function of k prime as e of k prime. This is, I used exponential, but using cosine, it's written in this way. And I claim that for very small k, this is basically k squared. This is very important. This is important. Okay, so this is the okay, this is a basic equation we got. So I the same thing with this ek. And then what we do is again standard. I multiply both hand side by e to the minus iku, sum over u, and divide by L over d over 2. Okay, and then L to the d over 2. And then the left-hand side, for the left-hand side, I think we use probably this or this. Anyway, one of these things, the left-hand side becomes exactly this. And right-hand side is just, if you simply compute, you get this. Okay, so you can solve for G tilde and you get this. Okay, and now you just plug this into the inverse Fourier transformation and you have this. Now, again, this is standard. I want to take the infinite volume limit where L goes to infinity. Then I claim that this summation converges to this Riemann integral. This is, again, very simple. If you recall this definition of KL, and then if you, as I said, K runs between roughly between minus pi and pi. And if you make L larger and larger, this, approaches sort of continue. And this exactly converges to this Riemann integral. Okay, and you can write it this way. Okay, so by taking infinite volume limit of this, we get this exact expression in terms of integral. So I can let me write this as id of h. Okay, and then let me go back to this spontaneous magnetization. As I said before, the spontaneous magnetization is written in this form. You take infinite volume limit in this. But now we know this. We know this explicitly here. So actually, we know the infinite volume limit of this explicitly, like this with this integral. So this is written in this way. So the only thing we have to take is this h going to 0 limit. So this is IDH, and if you substitute h equals 0 here, you get this. And so actually, I don't want to evaluate this carefully. I'm just interested in whether this integral is divergent or finite. That's the only thing I want to know. So for this purpose, you can just consider this very rough approximation, but okay, the divergence may occur only near k equals 0. So I need only to keep the form near k equals 0. So we this can be anything, but change the range of k like this and replace this by this form. Okay, then this is just basically equal to this simple integral, where this is the absolute value of k. And then you easily find that this for k d equals 3, this is just a constant, and it's of course convergent. And if for d equals 2, this is p inverse, and it's logarithmically divergent. Okay, so you see that this is divergent for one dimension 1 and 2, and it's convergent for d greater than equal to 3. Okay, so let's look at the behavior of spontaneous magnetization. And suppose that d is greater than equal to 3, and then we know that this part is finite. Okay, so I don't know the value, but this is anyway finite. And then this tells you that for very, very large beta, this is basically 0, and this spontaneous magnetization is very close to 1. Okay, spontaneous magnetization is exactly equal to 1 at 0 temperature. So this tells you that spontaneous magnetization takes value close to the ground state for very large beta. This is very natural, and this suggests that the ferromagnetic order is stable in these dimensions. Okay, what happens in dimension 1 or 2? Well, we see that this is divergent. So this doesn't tell us much, except for the fact that the approximation failed. Okay, the approximation failed because of the infrared divergence. Here we had divergence from here near k equals 0, and you call it infrared divergence. Instead, if you get divergence from k equal infinity, you say that we have ultraviolet divergence. I think this is an ancient expression, but we still use it. So and physically speaking, small k corresponds to large scale. So this means that we have divergence from large scale fluctuation. Anyway, so we have this large fluctuation, and the approximation fails. And this strongly suggests that the ferromagnetic order is unstable, even at very large beta in these dimensions. We already know this rigorously from the Hohenberg-Mermin-Wagner theorem, but this bold approximation, the Gaussian approximation or harmonic approximation, tells you the same thing. We now study the correlation function at magnetic field, and well, this is the main subject. And okay, so we are interested in this correlation function. For safety, I have positive magnetic field, and we have seen that this correlation function is equal to this expectation value. Okay, and again, by using the special property of the Gaussian integral that I'm going to prove in page 15, you can exactly rewrite this like this. Again, this is strange, so we are interested in the expectation value of this exponential, but we argue that this is exactly the same as the exponential of this correlation function. Okay, and now I will show that this is well defined even for h equals 0, so I'm going to evaluate this for h equals 0. So this is something we want to evaluate. And first, this looks complicated, but it's useful to rewrite this like this. Okay, again, we regard u and v as fixed, and regard this as a function of w. Okay, and then of course, by definition, this identity is just obvious. But anyway, we are interested in we try to find this quantity here, and of course, by using g that we already knew, this is written like this. Okay, and then by using the equation that determines g, that is in page 4. So yes, this is page 4, and this is the equation for determining g. And when there is h, so in our case, we don't have h, so this determines g, and we have two g's, so take simply the difference, and you get this. And of course, now you are worried about this equation because delta, this lattice Laplacian, has 0 as its eigenvalue. Then this matrix does not have its inverse, okay? Then this kind of equation is, of course, very dangerous. But in this case, we are safe. Why? Well, as viewed as a vector here, so recall that u and v are fixed. So as a vector, this is simply a vector which almost has 0 and 1 for u and just 0 and -1 for v, okay? And this vector is, of course, orthogonal to this eigenvector 1, 1, 1, 1, 1, corresponding to 0 eigenvalue. So this means that you can take pseudo inverse, or anyway, you can just decompose everything in terms of eigenstate of delta to solve this, and to find that this has a unique solution. Okay, so we are sure that this has a unique solution. So once you obtain the unique solution for this thing, and this is actually a Poisson equation, and then this can be written in this way. Okay, so our task is to analyze this equation. Okay, and of course, if you are good at Fourier transformation, you can again go to Fourier space and use k-space integral to analyze this. But I want to take easier way and relying on the analogy with something we already know very well, that is electrostatics. Okay, and so now, as I said, this is nothing but a discretized version of Poisson's equation for electric potential in the charge configuration where you have charge q at position u and charge minus q at position v. Q is actually 1 over beta. Okay, and okay, and so this is electric potential, and then this is the potential difference between the site u and site v. Okay, and this difference plays the essential role here to determine the correlation function. Okay, so our task is to obtain electric potential phi and take this difference. Okay, and again, you can do it by using k-space integral, but analogy with electrostatics is sufficient. For example, if you go to d equal 1, and then this discrete Poisson equation is very easy to solve, and you get an electric field in between two charges and nothing else. Well, this is the same as the standard problem in 3 dimensions. You have 2 plates which is charged in positive and negative, and you only have electric field in between them. It's exactly the same. And anyway, you can compute this, and then the difference can be computed this way. Okay, this is exact. We are not quite exact for higher dimensions, so we are not very rigorous, but this is not a very rigorous part of this lecture, so I'm happy with this. But if we want to be rigorous, yes, please go to Fourier space and do that. Okay, so let's consider 2 dimensions. Okay, and for some reason I want to be in infinite lattice now. And now you consider electric field generated by a charge at u, single charge at position u. And then you know that in 2 dimensions, charge electric field decays like this, so it's 1 over distance. And then the corresponding potential is log. Okay, and so this is a standard part in usual electrostatics. And here, usually you have divergence at the origin. But now we are working on a lattice, so there's no such divergence. You get some constant. Okay, so this is for this configuration, and for this configuration with negative charge, similarly you get this potential. Okay, these are potential for this and for this charge configuration. And then what we want is the sum of these 2 things, so you just sum over them, and what we really need is this difference, and so you simply plug this in and compute, and you get this. Okay, this is the most familiar case in 3 dimensions, and then you know that electric potential decays like this for this charge configuration, like this for this charge configuration, and again you don't have any divergence at the origin. Okay, and then this is what we want, and the difference by using this is computed like this. Okay, so now we are ready to evaluate the correlation function by using these results. Okay, we know how this part behaves. And so in d equal 1, you just plug this in. Note that this is positive. Okay, actually this is always positive. So we always get some decay. And in one dimension, we just plug in this and you get this. And you see this is the distance, so we have exponential decay. The correlation length depends on beta, but anyway, we have exponential decay. In 2 dimensions, now we know that this difference behaves like this. So I just plug this in here to get this. And since we have log, you can rewrite like this. And then now we have power law decay, and this exponent depends on beta. Okay. Finally, in d equals 3, it's the simplest case. You get this. And if you let this large, and this basically vanishes, and it converges to this finite value. Okay, non-zero value. So this means that in one dimension, this Gaussian approximation leads us to this exponential decay. And in 2 dimension, we get this power law decay. And in 3 dimension, we get long-range order. Okay, so this is the observation made by Wegener a long time ago, and by using this Gaussian approximation. And this suggests that something very interesting is happening in 2 dimensions. And of course, this is not at all rigorous. This is totally uncontrolled approximation. But in part 4, we're going to prove rigorous results, that the rigorous upper bound corresponding to this. Okay, so that's basically the end. And now, as I promised, I'm going to discuss the Gaussian integral. Okay, and so I want to prove 2 interesting inequalities that I discussed in page 6 and page 10. Okay, so for this purpose, I will discuss general Gaussian integral here. So lambda here is simply a finite set, and this A is any real symmetric matrix with positive eigenvalues. Okay, then I consider Gaussian model with this weight. So this is our partition function. Okay, and actually by diagonalizing this, you can exactly compute this partition function, but we don't use this. Okay, our expectation value in this case is defined like this. Again, the same weight, and this is normalization, and here you put something that you want to take the average up. Okay, then I argue that we have this equality for any complex constants AU. Okay, and so again, so this is actually the most general equality corresponding to these things. So here you have, this is a random variable. So here you have average of this quantity. Okay, and then we claim that this is exactly equal to the exponential of 1/2 of sum of this thing. And here you have this 2-point correlation function. Okay. Okay, once you prove this, then it's easy to justify these things. So now suppose that we fix V, and suppose that AV equal Y, and set AW equals 0 for all other W. And then the left-hand side becomes simply this. And for the right-hand side, you only have to consider U and V, which is equal to V, and then you have 1/2 I squared and 0 V squared, and so this is exactly what we had. For this thing, I fix U and V. I fix U and V and set AU to be I and AV to be minus I, and W equals 0 for other W. And then the left-hand side is this, and you just carefully compute the right-hand side, and you find has the precise form that I mentioned. Okay, so that this proves these useful equalities. So now we want to prove this equality here. Okay, that's what I do in the next page. To prove this, I will prove this equality here. Okay, and with this, we get this equality. How do you do this? Well, first of all, I assume that this has been proved, and then I'll consider this 2-point function. Okay, and then this can be obtained from this formula like this. So you differentiate, you assume these AU and AV are real variables, and you differentiate this with respect to AU and AV, and finally set all A to be 0. Okay, and then you just by differentiation theta U and theta V comes down, and by setting A equals 0, this goes to 1, and you get this equality. Okay, and here you use this. Okay, you use this, and you just compute, and you note that since A is real symmetric, A inverse is also real symmetric. By using this, you will easily find that this is A inverse of UV component of A inverse. Okay, so but once you have this, then you can substitute. You can yes, substitute this here, and you can replace this with theta u theta v, and then we get this equality. Okay, so how do you prove this? Well, this is not very difficult. First of all, I claim that for any BU which is complex, this integral here is exactly equal to z. Okay, and if b were real quantities, then this is just obvious. You just make the change of variable. But and when b are complex, then it's not so easy. But you go to you consider something like called complex Gaussian integral, and you will still find that you get the same result. Okay, so we use this, and then since this is arbitrary, we make this choice. We choose BU to be AV times A inverse UV. Okay, or since A inverse UV, this is A inverse is also real symmetric, you can write the same thing in this way. Okay, and then you consider this part. You consider this summation here, and you simply expand and you get this. And this is just this. And for B, you substitute here this one. Okay, and then you have A inverse and A, so you simply get A theta. And for here, you plug this in here. And then again, A and A inverse cancel with each other. And for here, I think here you use this, here you use this. And then you have A inverse, A inverse, so you get one A inverse and you have this. Okay, so you will see that the left-hand side, yes, the left hand of 3 is precisely written like this. Okay, so this is, we have, so but by using this, yes, this left-hand side is precisely this. Okay, and we see that this is equal to z. Okay, now this part does not depend on theta at all, so you just bring it here, and this part, this is normalization, you just bring it here, and then this is a weight, and this is the this is a quantity that we want to calculate expectation value, and you precisely get this. Okay, so that is the proof. And so this is basically the end of the whole story. But since I talked about Gaussian integrals, this is a useful exercise. And in this appendix, I want to talk about something called Wick's theorem. We don't use this, but probably it's better knowing this. Let f theta be any function of theta. Then the expectation value of theta u times f theta is exactly written like this. Okay, here you have 2 points, so sum over w, 2-point function, and the expectation value of this derivative of f. Okay, and it's easy to prove this. So this is exercise, so I would like you to prove this, but the trick is to use the integration parts as we did in page 3, and also use this page 16 too. What is this? Well, this is an important relation. This 2-point function is equal to A inverse. This is the point, and so you can replace this by A inverse UW. Okay, so instead of showing this, you want to multiply A from the left, and then it's not difficult to prove to showing the resulting equation. Okay, so I hope you will do this. And then as an application of this, here is one identity. Okay, so suppose that this is theta u1 and this thing is f theta. Okay, and then you use this. then you sum over W, and for most W, nothing happens. But if W happens to be equal to U2, and then you have this 2-point function, and from this part, you have this, okay? And then when W is equal to U3, you get this, and when W is equal to U4, you have this, okay? So probably you have seen this kind of diagram before. So the left-hand side is a 4-point correlation of 4 points, U1, U2, U3, U4. And this identity tells you that it can be decomposed as a sum of 3 things. And this thing is you just have correlation between U1, U2, U3, U4. Here, U1, U3, and U1, U4. Okay, so you can regard this as a partition into distinct pairs. Okay, so these are pairs, these are pairs, these are pairs. So this is, you are summing over three different partitions of these 4 points. Okay, and you can easily generalize this. So for suppose that n equals 3 and you have 6 points, U6, U1, and U6, U6. So here you have 6-point correlation function, and by using this once, you have here 2-point function, and here you have 4-point function. And for this 4-point function, you can use this. And then in that case, you will get, I think you will get sum over 15 terms, which corresponds to all possible partitions into distinct pairs. Okay, and of course you can generalize this to general n, and in this case, yes, this is summed over all possible 2n-1 double factorial different partitions. Okay, so that is called Wick's theorem, and I think this is one of the easiest way of deriving this kind of identity. Okay, so that's all for part 3. Thank you very much for watching. And in part 4, we are going to prove Maclaurin-Spencer theorem. Okay.